What did the fish say when it swam into the wall? Damn! And that's exactly what we're talking about in this 8.4 topic. We're talking about dams and hydroelectric power, and we're also going to solve some problems with that, and we'll also solve some problems with wind power, or what you might know as windmills. Some very simple reading, or maybe some common knowledge, will tell you that in any hydroelectric dam, you're usually going to have your turbines at the bottom of it, and it's this water stacked up that is going to provide the power as the water goes through the dam. So let's say in a sample problem, you know that the flow rate through the turbines is 500 liters per second. It's a 40-meter high water level above the turbines, and you want to find the power. Now, don't go looking through your IB data booklet to find an equation for this, because there isn't one, which is kind of disappointing. But you just need to know that the energy behind the dam is gravitational potential energy, and you know that that can be calculated by MGH. You know the definition of power is energy, in this case, your GPE over time, or your MGH over time. Now you may think, how am I going to know a mass of water when I'm usually giving things like volume? Well, you should know that density is equal to mass over volume, and the density of water, there's a couple different ones that you can choose from. You can say that it is 1 kilogram per liter, or it's 1,000 kilograms per cubic meter. It depends on what volumes you're dealing with. Here we're dealing with liters, so that is going to make this the more useful density for us. And what we can say is, if we rearrange, that the density times the volume is going to equal mass. And that we can plug into our equation right there. And so power is going to equal the density times the volume times G times H times T. Now, check this out. We've got a volume over time, and that, my friends, unbelievably, is our volume flow rate. And now it's just a matter of plugging in to find this volume. You know that you're going to have 1 kilogram per liter, flow rate of 500 liters per second. G is 10, and your height is 40. I've left out all the units just for the sake of speed there. And then if you do this, you're going to get something like about 200,000 watts as our power. As a small note, that 40-meter height that you put in assumes the water level is constant. If the water level drops continuously, then you may have to cut that height in half. With windmill problems, you have to look up a crazy equation, so take a minute, read this problem, see what you can find in your data booklet, and give it a try. Now, hopefully, you saw that the power equation that you're going to use is P is equal to 1/2 A times this equation here, where the A, hopefully you know, is standing for area, taken in by the blades. This is the density of the air, and you can probably guess that this little v is the velocity, which makes sense. Now, you have air that's going through at a high speed, and then it slows down. And where do you think that kinetic energy went to? It went to the windmill. So what we're going to do is we're going to find the initial power of the wind, which was big, minus the final power of the wind, which is smaller, and the difference will be the power that we're looking for of the windmill, the maximum amount it could get. So we're going to have 1/2 times the area, which is going to be pi times the radius squared of the windmill times the distance times v cubed. And we'll do this twice because we've got two different values. And we'll plug in our numbers. The radius we know is 1.5 meters squared. Our first density is 1.2. I'm going to start leaving out units. And then the velocity is 8 cubed. And then over here we've got so that same radius, because the windmill doesn't change. 0.5 squared. The density has gone down. When air slows down, its density does tend to go up. And its new velocity is going to be 3 cubed. Once you solve this, which take a minute, put in your calculator if you haven't already, and solve it, you should get something like 2,171 watts minus 171 watts, and that should leave you with about 2,000 watts as your answer for the maximum power of the windmill. In reality, it's going to have less than that because it's not going to be 100% efficient.